All right, so it's good to see you again on Friday. I know you cancel this classes on Wednesday and Thursday cancel, but now we're back in the lecture on Friday. Those of you who already got my email, right, for you're taking also the lab courses, right? And then if you're asked to come to next week, you can come. If you choose to do some online assignment, just let me know. But here's the thing. I also posted the syllabus today, actually this morning. I just did. I want you to just go ahead look for the syllabus on Canvas and see. So I hope you guys are watching my lecture video on YouTube channel, but it's basically the same thing. Just 2 exams, one midterm exam can be dropped because the percent score of your final exam will replace it. Okay, and also we're gonna have first exam the beginning of October. So it starts at actually 5th. That's Monday. So this 5th of October. This is Monday. So the Wednesday is actually obviously 7th and 9th. And you guys in Friday lecture part, right? So you guys will have first exam on 9th of October. That's your first exam. The second exam, your second midterm exam will be, let me see, 16th of the week of November. So that's obviously Monday. So the Wednesday is 18th, Friday is 20th. Okay. So your second exam will be on 20th of November because you guys in Friday parts. So if you guys watching this, if you're in Monday or Wednesday, they come either Monday for 5th of October, 16th of November. If you're in Wednesday part, 7th of October, 10th of 18th of November, and we are in Friday, so it'll be 9th of October, 20th of November, we're gonna have a midterm exam. Sounds clear, right? Okay, so make sure you guys go and find the syllabus. We can also look it up. And also the final exam, we're gonna do it like an online exam on campus. The reason why I wanted to give you some extra credit assignment, you guys remember this? Because I just want you to practice on how you can answer the question on campus for your extra credit. And you'll be more prepared for the final exam, which you're gonna take it on campus as well. So the final exam will be on like a quiz tab. It's not available right now, but I'll make it available for the student. So you can actually go to campus and click the quiz tab on the side, on the left side of your campus browser. You'll find the final exam, or actually soon your extra credit assignments. Okay. So I think that's the only way because we can meet after Thanksgiving. So once again, the final exam can be really game changer. So if you keep trying until the end of the semester, you'll do really well in the class. And which that happened in the last semester. I mean previous, not just last one. Okay, sounds good. So if you have any question, just let me know. But you can find all the information in syllabus on Canvas. It should be all consistent with what I've been saying in the previous lecture anyway. Okay? So there's not much thing you need to worry about. Just find more detailed information if you want to in the syllabus on Canvas. Do you have any question other than what I just told you? You good? Okay. All right. So just one more thing. I posted one lecture on Canvas, not on the YouTube channel, because I used some of the picture files of the textbook online copy. So, it should be okay, but I didn't want to have some copyright issue. Normally it's not a problem, but still. So I just put it on the Canvas for that specific course because it was about the confirmations. So this is just something I also want to just briefly talk before I move on to chapter 4. But all detailed information about this one on Canvas video anyway. So this one specifically on Canvas, not on YouTube channel. So please find this one on the Canvas. This is better if you look at on the Canvas lecture video because this is including a lot of drawings, which I'm not so good at. But let me just point out just a couple important things, and then I'll move on to chapter 4. Okay. So the last part of chapter 3 is about the confirmations. So confirmations is the change you can make. Can be made by rotation of your sigma bond. Okay? Or you can say single bond, it's the same thing, right? So whenever you have certain like compounds, like you have, okay, you have this one, we call this ethane, right? So this is what it looks like. But once again, for this chapter, most importantly, the alkane can be always rotated because the single bond have a lot of freedom so they can be rotated. So if that is happening, there's another way to draw this this compound. The first one is what we call sawhorse projection, or you can say representation. The other one is Newman projection here. Okay, sawhorse or Newman projection over here. So this is ethane, but if you look at from like a top side view, this will be more looks like this. So those two carbons are in this, and you can try to draw okay, and you can draw the okay. So as you can see, if you look at the that compound from this view right here, you're actually going to have those bondings on this carbon. Maybe you can call this the carbon number 1, carbon 2, heading the other part. So this is like this one going this one, this one, this one, and one carbon. On the back goes this one and this one and this one. So they're gonna go. So it's really hard to see. Whenever you do, this is sawhorse projection here. So normally what we do for this one is Newman projection is this is small dot here. This is the front carbon. So this is this carbon right here. Okay, and I draw the bondings to the hydrogen, maybe like this. Okay, and I'm gonna draw bigger circle, empty bigger circle, right on the center. That big center is this carbon right here on the back. Okay? So now you're looking at the top side view for this one. This one you just confront it right through, right here. Okay. So this is one axis is right into your direction of the site. So this one is the back carbon here, and the hydrogen on this carbon goes here, like this. Kind of makes sense. Okay. So once again, you can watch the video later, but I just want to point out at least once before moving. So obviously, as you can see, this is better to show how much they're rotated on each carbon, so the front or back. Okay. So I mean, if you're good at drawing, this might be also just good enough. See, oh, I can see that. I mean, top side view, there we go. But for this one, you can actually tell how many degree or how much it was rotating on the other carbon so far. So normally we prefer this one, especially when we want to know how much it was rotated or so forth. Okay, makes sense so far? You good? Okay. So if that is the case, and now you guys wonder why we care about this one anyway in the first place, because of this. So most of the things, all the molecules are somewhat unstable. They always try to rotate, or eventually they try to find their most stable form anyway. Okay? So in that case, you have a two. I just showed you this one. Okay. So obviously those carbon-hydrogen bondings are nicely and efficiently spacing out from the 3D space because of the angles and also the rotations give us the far distance from each hydrogen carbon on this ethane compounds. However, you can always rotate it, right? So if that is possible, you can rotate it maybe here, here, and here. You can also do this one, right? If you rotate it, okay, right? So if you rotate it, either the back or front carbon, they're going to somehow like an overlap on the one side and the one face. That's what we call. It's same as eclipse. You know, have you seen the eclipse before? Okay. Eclipse. So it's eclipse conformation. And when it's nicely even out by rotation, we call this staggered conformation. Okay. So obviously, most of the staggered conformations guarantee the more stable form of the same compounds. But when we rotate it, this will become somewhat unstable because of the distance between those bondings are closer now, and they need to somewhat experience the discomfort because they now need to compete for spacing, limited space. So obviously, this is somewhat unstable. This is quite stable. And there's one word that will be on the exam for sure. This is very important. So I want you to remember this one. Here's the thing. If this is stable, if this is unstable, that means whenever you rotate it, you need to so maybe from here to here, no problem, right? But here to here, they will resist, right? Because they want to stay in stable form. If you try to rotate it, they don't want to do it because they want to be staying in the stable form. So that means you need to put energy to make it happen. There's no free. They're not going to do this for free because they don't want to be unstable. So that amount of energy you need to invest to make this in the eclipse conformation we call torsional string. Torsional string. Torsional string. You know what torsion means, right? Torsion simply means you're twisting it. You're twisting it. But when so twisting is more like a rotating, right? When you rotate it, you have a resistance that you need to experience when you try to rotate it. Then you need to use a certain amount of energy. So this is what we call this torsional string. Because this amount of the energy you need to use to make it twisted, or you can say rotate. It kind of makes sense, right? So far so good? Perfect. So if that is okay, I'll just give you a few more examples. And there will be, okay. But once again, there will be about half hour video on campus. You can check it with the nice image. But here's the one thing I can still tell once more before we go into chapter 4. So if that looks good, let's try to look at the propane. Okay, so now you have 3 carbons. Okay. Obviously, this one has let me show you one drawing over here. So whenever you have the hydrogen over here, right? So when you try to look at this one, you can also say this one has 3 hydrogen. Okay, can also say so it looks like this. Okay, so do you know what this means? Wedge and the dot lines. Do you know what those are in Jenkin 2? Kind of. So the wedge is more like a if this is the plane, the wedge bonding is going forward. So this bond is not on this plane of your backboard, but it's going this way. The dot is going back side of this wall. Same thing here. This hydrogen comes this way, the dot line here, going back side of this room over here. And the one on the just plain line over here is just right on this plane of the backboard right there. So this is some 3D image over here. The only difference that you can get from propane instead of ethane is your additional methyl group here. Okay? So let's try to do it in let's try to do it on the Newman projection here. So maybe this is the front carbon, this is back. You can say this is here, okay? But there's 2 hydrogen on the front carbon here. Okay. And this is the carbon right here. Okay? This carbon has this way, right? Okay, so this is also staggered conformation. As you can see, they're all nicely spread on this side of this face of the compounds. If you look at right confront the compounds and your eyesight. So this is pretty nice, but whenever, let's try to, and you also can draw the eclipse conformation, right? So when you try to rotate it, you can also try to do this one. I'm sorry, my drawing, I knew this coming, but once again, you can also check this in the canvas. Whenever you did this one, we find out those will have about, so I just told you there will be a certain amount of energy for rotating to make it in the eclipse conformation. But the amount of energy for this one, for overlapping the hydrogen, carbon hydrogen bond on this side and this side, was just smaller than this one. The methyl groups and also hydrogen, about 6 over here. So now the scientists now thinking, oh, maybe it's not just about the torsional string, but there might be something else. And it's just because if you think about the hydrogen and methyl group, obviously the one big change you can see is the size, right? It's much bigger in size than hydrogen. So if it's more bulkier or it's much bigger on that group on this carbon, that makes the more strong static hindrance because of the size. And if you think about the electrons that around those each atoms, especially on this carbon is bigger than hydrogen, and also it has the 3 other hydrogen on that carbon as well. There'll be more strong, I can say electron cloud there. So the competing on this space with the hydrogen, with the methyl group, will be stronger than these two because of the size. Makes sense, right? So maybe it's not just about just twisting it on the eclipse conformation, but also the size matter, and we're gonna call this static strain. So just the way they are in the size, there's going to be somewhat van der Waals interaction there with this electron kind of magnetic hindrance, the interactions. It caused us to use bit extra energy as well too for that one, because it's the two competing with the even smaller space now, because this one is bigger. Makes sense? Sometimes you good? Okay, perfect. So in this case, we also have a torsional strain, but and also the static strain because of this method over here. Okay, so now the question is, okay then, how about butane? Okay, so butane, we have carbon, 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 carbon over here. Okay, so let's say you have, okay, and we're gonna look at it in this way now. Okay, for Newman. So maybe we do this again. So front carbon, back carbon, doesn't matter. I'll just draw this one here. Okay, we can choose. Okay, like this. Okay, this is okay, right? This is pretty good. I think this is quite stable because, as I mentioned, to experience the least amount of the static strain, also the least no discomfort like torsional strain. Those two methyl groups on each different carbon, front and back carbon, are like far away from each other, which will show you 180 degrees. This is the most far rotation they can get from each carbons over there. And this is also obviously in staggered conformations. So in this case, this butane will have a most stable conformation because of this methyl group are heading opposite directions, which is quite nice for them. They still have they don't have to compete for the space or any static strain problem. So we call this anti-stagger conformation. This is the most stable form of the compounds. Okay. Whenever you rotate this one, among this the Eclipse version of this one. And whenever you're going to have the worst scenario will be this one, right? Worst scenario will be okay. So the worst scenario will be this one. So this will be the least stable, the most unstable conformation, because these two methyl groups on each carbons are now experience not just the torsional strain, but also the greatest possible the static strain over here. So does it make sense? So this will be the most unstable or the least stable conformation of the compounds on here. Okay. So that's pretty much it. Let me actually go over. So there's another one. We call this the. Here's one more thing. Let me find the. It's really hard to. So this is actually something I wanted to go over, but just make sure you watch the Canvas video once more, because I don't think we have a. Okay, so yeah. All right, so let's move on to chapter 4. So chapter 4 is it's all about the cycloarcane. Okay, so cycloarcane. So one thing what we need to know about this one, they will be in the ring structure. So whenever you try to draw like a butane, simply means there's 4 carbons and the linear shape. So if you fill the hydrogen on each carbon, this is what it looks like. Okay, this is what it looks like. So make sure we have 4 carbons, but obviously, if you record something in Gen Chem 2, that is the H10, even though you don't count them, because we follow CnH2n plus 2. Do you guys remember this? Butane 4. So means the butane, it means there are 4 carbons, right? 4 carbons here. Okay, we have 4 carbon here. That you also have numbers for the hydrogen is 2n plus 2, so it'll be 2 times 4 plus 2 will be 10. Okay. So that's how we know C4H10 over here. Okay. But whenever you do cyclo, the butane, it actually in the ring structure. So now it has a structure looks like this one. Okay. So if you do fill the hydrogen, even though there is no double bond or triple bond, now it actually becomes CnH2n. If you count the hydrogen over here. So because of the ring structure, they actually going to have 2 less hydrogen than is in the linear shape. Because now the other carbons, this carbon was with the other carbons in the ring structure. This is why cyclobutane will have a chemical formula C4H810 because it's in ring structure. This is something you also sometimes confuse, so please remember this, because even though there's no triple or double bond, if it's a ring structure, aromatic structure, cyclobutane, they might have just CnH2n. So CnH2n is actually the one with the 1 double bond, right? Alkene. But also for the cycloarcane, it also has the CnH2n. Not because it has a double bond, but it's a ring structure. Kind of makes sense, right? The carbons are the 2n. So think about those 2 carbons are making one like this, make a ring. So in that way, they lose 2 hydrogen there. Makes sense, right? Okay. All right, so that's pretty good start. So obviously, what you need to do is when you try to find the ring structure like this, all you need to do is try to count the carbon. 1, 2, 3, 4, 5, and 6 over here. Okay. So this is obviously hex, means your base that represent there are going to be 6 carbons in your main structure. So that is, but there's no double bond, so we're also going to put A and E at the end too. But it's in the ring structure, so we're going to just put cyclohexane. That's all you need to do. Okay, it's for this one. So whenever you have some type of teaching group, like method group over here, we're gonna do the same. Did you guys watch the chapter 3 one? the nomenclature is the same. So whenever you look at this one here, so what we're missing here is that this is a part of prefix, but you have also substituting for prefix and locant here where you can tell where the location of the method group here. That would be also same. We try to put the this possible number for the location. There will be 1. So if you count the carbon from the other side, maybe 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, or 1, 2, 1, 2, 1, 2, 3, or but always you choose the least like a possible number that is 1. And you can put 1 methyl cyclohexane. So if you have only one substituting group on your like a main ring structure, element structure, if there's only one, you don't actually put the locant there. Can you guys guess why? If there's only one substituting group, you don't actually have to put the locant there. Because the people just it doesn't matter. There will be no 2-methyl cyclohexane anyway. Like I said, you need to put the least possible number for the substituting group, right? But why would you put 2 here? And if you just rotate it, so now you can say it's maybe 2, but if you just rotate it, the same as 1. So if you have only one substituting group for the ring structure, people just know where it is. So for cycloalkane, if there's only one substituting group, just ignore about the locant, that's fine. I mean, I don't think they even use it anyway. So we could just kind of call this methyl cyclohexane. Makes sense, right? Good. Okay, perfect. So then, okay, just one more before we do 2 substituting group here. Sometimes this is quite, I think, interesting. So if you have a ring structure here, which is 3 carbon, you have also the substituting group, which is 4 carbon. So in your textbook, what it says in your textbook is when you try to find the substituting group and also the ring structure of your compound, there are 3 carbons here, 4 carbons here. So make sure which one is more dominant. Either you're gonna call this 1-cyclopropyl butane, or you can say butyl 1-butyl cyclopropane, or either way, right? And in this case, in your textbook says find the longest carbon chain. So that will be the main part of your compound. And this is your substituting group and so forth. So in this way, we're gonna call this 1-cyclopropyl butane. But here's the one thing I wanna tell you. If you just try to find the compound name 1-butyl cyclopropane is also there in the chemistry nomenclature. So I think it's preferred, but I don't think it's absolute rule. But this is just for your information. So the basic rule is to find the main parent, your parent. The one is the bigger and major part of the compound, which is this one. But in chemistry, it's not really absolute rule, I guess, in my opinion. You can always find either 1-cyclopropyl butane, or you can always find 1-butyl cyclopropane. Either way actually is possible. But obviously the parent's base name is maybe more preferred anyway. Just for your information. I think it's just because of this one. Whenever you do the chemical reaction in the lab, the most important thing is not about we follow the one is bigger and longer because they will play the major role of certain chemical reactions or the characteristic of the compound. But still, sometimes maybe people think that, oh, even though this is parent, this cyclopropyl will do more, contribute contribution to the characteristic or certain type of chemical reactions. So I think this is more important. Then that chemists will call this what? Butylcyclopropene. Something. So I think it's more like, I think that's the reason why. Actually, I don't know why. But one thing I want you to tell you is whenever you look at the compounds, you look at the size of each group, but also how functional that each group is. And they will sometimes determine how your name can be for other parts of your nomenclature. Make sense? Just for your information. But I'm sorry to confuse you. But always basic rule is find the bigger one. That needs to be apparent groups. Just for your information. Oh, it's wasting a lot of time. Sorry. So okay. So whenever you have a now cyclohexane, now we're talking about 2 or 3 substituent group here. So let's try to do 3. Maybe you can do 3. We can do. This is an ethyl group. There's another methyl group over here. Okay. So in here, we're gonna do the same thing. We try to number the carbon on this main the structure. So we'll do 1, 2, 3, 4, 5, 6. So that will give you local number 1, 3, and 4. Okay. But if you count the carbon from here, maybe clockwise, 1, 2, 3, 4, 5, 6. That'll be 1, 1, 4, 6. Okay. So maybe I don't like it. So maybe I'll do the carbon, number the carbon from here, but the counterclockwise. So that will give you 1, 2, and 4. And among all the possible the combination with the locants, this looks the least inside to me. Are you agree? Do you agree? Right? So now I decided to number the carbon from here and counterclockwise. Okay? Just to make the minimum possible, least possible number for the location of substituent group. Okay? So now but the rest part is the same as what we did on chapter 3. So we have 2 methyl group here, 1 and 4, okay? And you have 1 ethyl group at 2, okay? So we're gonna order this alphabetically too. So we're gonna add, we're gonna put the 2 ethyl and 1 and 4 dimethyl cyclohexane. Okay. This is the how you can. So once again, whenever you order this one, your substituent group in alphabetical order, this di doesn't count, right? So make sure they count as E, and this methyl group count as M, not D. Even though there are 2 dimethyls, still count as M. So that's why I put ethyl group first, E and M, and cyclohexane, and just make sure you put the location. And you also put the potato 2, di, potato 3, tri, potato 4, tetra, so forth. That's it. It's pretty much the same, right? Pretty much the same. Okay? Perfect. All right, looks good. So just a few more things. We're almost done. Make sure nomenclature in chapter 4 is not very important, so I'm gonna make it quite brief as I can. So one more thing. So how about we have 2? Like this. Then this is kind of tricky. Let me tell you why. So in this case, either you can count this from here to here. 1, 2, 3, 4, 5, 6. So that's 1 and 2. But the problem is, if you count this carbon from here to counterclockwise, there will be 1, 2, 3, 4, 5, 6. Right? That is still also 1 and 2. Right? So now, what should I do? same. You're always going to find the simplest possible rule for anything. So whenever you have this one, this is ethyl group, right? 2 carbons, the one, so it'll be methyl group here. And then you also, whenever you have a 2 possible combination, follow the one that is the alphabetically first prior as the lowest possible number. So that will become 1 ethyl, 2 methyl, cyclohexane. Okay? So if you, and this one is actually quite absolute rule. So there will be no like, 1 methyl, 2 ethyl group, ethyl cyclohexane, you cannot find it. But yeah. So whenever you have a 2 least number local combination possible for either case, try to find which one has comes first in the alphabetical order, and that group will have the lower number, which is 1, and the other one will take 2. It's kind of tricky, isn't it? But if you just keep practice a few more times, it will get become easier and easier so far. All right. There's only one scenario you can. There's only one scenario you can change this problem like this. Is the this one. Whenever you have double bond in here, okay. So if that is the case, I already mentioned before, but it's always good to follow the least possible number for your surname suffix. So now this is a cyclohexene because of your suffix, because of the double bond here, right? And this is the only time that you're going to put the this one, not just 1, but this will be 4. Okay, so this will be 1 and 2, this possible number, right? So it'll be 1, 2, 3, and 4. Okay, so this will be 4. Something like this, but this is the only time that overrule your locating your substituting group. That is also same that we did for the chapter 3, the linear ones. That maybe the suffix name always considered as most important part of your name. That's why in this case this now would be not 1 but 4 instead. Okay? But I will do this actually later because we're only doing the ones with the alkanes, cycloalkanes. But this is only for your just for your information. Okay. All right. Oh, okay. So time flies so fast today. So okay. Anyway, so there's only one more thing I want to mention before we finish. Is this one. So whenever you have dimethyl cyclopropane, okay. In this case, I think you don't have to also put the locant there because obviously the 2 on 3 will be always same anyway. So you ignore the locant. I think it's okay. And if you look at this one over here, you can also put the methyl group right here. Okay, like this, or you can put the other ones like this. Okay, so here's one thing. I know I already told you in chapter 3 that the single bond can always rotate, right? But if you actually think about in a ring structure right here, they're actually those 3 carbons are linked together in a ring, right? So, and also beside the double or triple bond, the one with, even though they're all in single bond, if they're in a ring structure, you cannot also rotate it too, right? If it's a ring, unless you just tear it into the two carbons on the ring, you still need to keep the ring structure, so you can't actually rotate it because in the ring. Because you see the magician do some magic, they do something without passing the part of the ring. That was awesome. But anyway, so that means this cannot rotate. So in this case, I don't know if you guys watched or remember one of my lecture. This is sometimes we're gonna use trans and cis isomers. It's one part of your stereoisomers, which means they're also going to share the same bondings here and here, and here and here, all same bonding between each carbons in the cycloalkane, but only the orientations, the way they are on this side and this side is different. Okay, so if you look at the ones and those, the methyl group on the opposite side, we're gonna call this trans dimethylcyclopropane, and the opposite side. But they're looking at on here, on the same side, here and here, we're gonna call this cis dimethylcyclopropane.